Welcome to this lecture series in linear algebra. In this lecture, we'll look at the notion of diagonalizability of an endomorphism, and we will look at a criterion to decide when a given endomorphism is indeed diagonalizable. So we will need some basic facts that we have proven earlier. So one of them is the following. If T is an endomorphism on a vector space V, and MTX is the minimal polynomial of T, so this is the minimal polynomial of T. So basically the statement is that the minimal polynomial of an endomorphism splits over the base field of the vector space if and only if the endomorphism is upper triangulable. Alright, and the other is the primary decomposition theorem. So if the minimal polynomial of an endomorphism is factorized into powers of distinct irreducibles, so these are pairwise distinct irreducible polynomials over the base field, then the vector space V is the direct sum of the kernels of these powers. So yeah, we will use these facts. And now let us get started. So just like we had the notion of upper triangulability, we have a stronger notion of diagonalizability. So first of all, we will define what is a diagonal matrix. So an n cross n matrix M, whose ijth entry is aij, and F is some field over which this matrix is defined. So each aij is a member of F. So an n cross n matrix M with ijth entry aij is said to be a diagonal matrix if aij is equal to 0 whenever I is not equal to j. So only the diagonal entries are potentially non-zero. Every other entry is 0. So for example, the all zeros matrix, meaning each of the entry is 0, is also a diagonal matrix. But for instance, this matrix is also a diagonal matrix where only the ones appear, only once, the diagonal features only once, and everywhere else you have 0. This is called the identity matrix. Okay. So I don't think we need to look at examples of this. It's a very simple definition. So now we will define the notion of a diagonalizable endomorphism. So fix an endomorphism over a vector space V. We say that T is diagonalizable if, one can guess, there exists a basis of V such that the matrix of T with respect to B is a diagonal matrix. So once again, there is no such thing as a diagonal endomorphism. There's only diagonalizable endomorphisms. And if one basis works, there is no guarantee that other bases work. In fact, most of them will not work most of the time. But anyway, so it's clear that every diagonalizable endomorphism is upper triangulable. So that I leave you to. There's nothing to figure out there. Okay, so we have this very simple, very basic lemma. So it says that an endomorphism is diagonalizable if and only if there is a basis, each of whose vectors is an eigenvector. This is an if and only if statement. And let me just prove one direction of it because it's a very, very simple statement. So suppose B is a basis of V such that each Vi is an eigenvector of T. Want to show that T is diagonalizable, and it's very simple. So say TVI equals lambda I Vi for I equals 1 to n. This is legitimate because each Vi is an eigenvector, so for each I there is some lambda I for which this equation holds. And now the matrix of t with respect to b would look like only lambdas on the diagonal, everywhere 0. So that's clear, and therefore t is diagonalizable. And you can just retrace this to prove the other direction. So that we have. And now for the main theorem. Just like we had a criterion to decide upper triangulability of an endomorphism by looking at the minimal polynomial, we have a criterion to decide diagonalizability of an endomorphism by looking at the minimal polynomial. So fix an endomorphism on a vector space V, and let's say mx is the minimal polynomial of t. Then the endomorphism is diagonalizable if and only if the minimal polynomial splits into distinct linear factors. If we slash this out, then what we get is the criterion for upper triangulability. So with this stronger adjective in front, we get diagonalizability. And this just means that the minimal polynomial of t looks like let me not use lambda 1. So it means that minimal polynomial looks like this for some pairwise distinct a1 up to ak. That's what it means to split into distinct linear factors. Okay. So, yeah, which direction should we start with? Okay, so first assume diagonalizability. So assume t is diagonalizable. We want to show that mx splits into distinct linear factors. So the fact that mx splits is clear because in particular t is upper triangulable. So we already know that mx splits. I'm not writing that. Okay, so let this be a basis of V such that the matrix of t with respect to B is a diagonal matrix with entries we denote like this. Okay, so I mean some of these may repeat. There is no guarantee that these are distinct. Some of these may repeat. That's okay. So what we will do is we will say this script E is the set of the values appearing on the diagonal. It is possible that E is a singleton, meaning the size of this set may be a singleton, in which case all of these are equal. But whatever, this is a set. And define this polynomial Px as this product, right? So this is how we define it, and let me just emphasize that this is not necessarily the same as, not necessarily Px is not necessarily equal to this product x minus lambda 1 up to x minus lambda n, because if there is repetition here, then we are multiplying that the corresponding polynomial only once. It is lambda is varying over a set, right? So it is the set of values that are here over which lambda varies. So if there is repetition here, we just count it only once. So let there be no confusion about that. Okay, and we claim that. It's a very, very simple claim. Pt is 0. Right? So to see that, you just show that PTVI is 0 for each I. And suppose, so let I in this be arbitrary. Then PT of Vi equals, this is T minus lambda I operated on Vi, but this is equal to that, and I'm being completely formal here. So this is 0 and that's it. This is 0 simply because of this matrix. So that's the proof that PTVI is 0, and therefore PTVI is 0 for all I, and hence PT is indeed 0. So this is just a justification for this claim. You can justify it in whatever way you like. Okay, so we have that, and therefore mx divides px. So thus mx divides px, and since px splits into distinct linear factors, mx also splits into distinct linear factors. Therefore mx splits into distinct linear factors. That's the proof of this direction. For the other direction, let assume mx splits into distinct linear factors. We want to show that T is diagonalizable. So say mx is equal to that for some lambda 1 up to lambda k in the base field, with them being pairwise distinct, right? By hypothesis, such lambda i's exist. And now by primary decomposition theorem, we have the vector space is the direct sum of these things. Okay, and now choose a basis of this vector space. This is a subspace and hence a vector space. So choose a basis b1 of this dot bk of this guy, and just concatenate those two. I'm writing it in somewhat sloppy fashion, but I hope you understand. So just arrange the vectors that you get here in one line, and that would be a basis of the vector space V. So this is a basis of the vector space V, and the matrix of the endomorphism T with respect to this basis will look like lambda 1, lambda 1, lambda 1 repeated how many times? This is repeated the dimension of this subspace those many times. Then you will see a list of lambda 2s, then dot list of lambda n's. So this repetition is happening whatever is the dimension of this guy, that many times this repeats, meaning this is the block size and this is the dimension of the second one, and so on. So this is a diagonal matrix. And with this, we have proven our main result. As usual, like, comment, share, subscribe, and I'll see you next time.